message that you're gonna have to send back and forth between the coordinator and the requester. The message is gonna have to go through this node, through this node, through this node, through this node. Okay. It's 5 hops. And if this is an infrastructureless network, where we have a peer-to-peer connection between all of those nodes, that's a lot of messages, a lot of overhead. So you may say, well, if you're on a wired network, a traditional distributed system, what's the big deal with sending a message? Well, this is not a traditional distributed system. If everybody's running on battery power, we gotta send a lot of messages back and forth, that stuff adds up. Okay, so we can reduce that overhead, that may make a lot of sense to do that. So we are not sending that explicit reply. Once number 1, who is presently accessing the shared resource, is finished accessing that particular resource, is going to reply to 2, who is waiting in its queue. Okay, if it's finished, go ahead, access the resource. Okay. Now, relatively straightforward, okay? However, who can drop off of this particular network and create a deadline?
The coordinator.
The coordinator. Okay, always if the coordinator drops off, we got a problem. Right, so we're gonna have to pick a new coordinator. Who else can create a deadline?
Anyone?
No, not in this algorithm. Decentralized algorithm, anybody can drop it off the network and create a deadline. Okay, here, if number 1, who is presently accessing that shared resource, drops off the network, it can't release the lock. If it can't release the lock, then you're dead. Okay, so these are 2 situations where, 1, 3, those 2 nodes dropping off the network, okay, or stalling or failing or whatever, creates a deadline. Okay. Again, with centralized algorithms, okay, we got that 1 point of failure. Another thing we have here is a bottleneck, right? So if we have a whole lot of resources or a lot of nodes that are on this particular network and they're all requesting to access something, Free is gonna have to handle all of that stuff. And again, if these are mobile nodes, they're running off battery power, that stuff adds up. Okay, we can't disregard that. So that's a centralized algorithm. Decentralized algorithm. All right, I'm not gonna go and read all that to you, we'll look at the diagram. What happens in a decentralized algorithm, okay, there is no coordinator, right, totally distributed. So if you decide that you want to access a shared resource, what you're gonna do is you are going to send a timestamp of your local clock off to everybody who is in the network. If whoever is in the network has no interest in accessing that particular shared resource at that time, it's just gonna reply back with an okay. It's gonna say, I don't wanna access it, I'm not currently accessing it, whatever here. Okay. Now, if you are presently accessing that shared resource, you just don't reply back with anything. Okay, so again, that implicit no, you don't reply back with an implicit message. If you and one other node, or at least one other node, are requesting to access the resource at the same time, what you're going to do is you're going to compare those timestamps. Okay, so here's a tie. Node 0, node 2, they both want to access that shared resource. So 8 has a smaller timestamp than 12, 8's gonna win that tie. Okay, so what's gonna happen is 2 is just going to reply back with okay. And once you have received an okay from everybody in the network, you can go ahead and access that shared resource. Okay. Now, are the timestamps on here an actual indication of who requested that shared resource first? Yes, no, maybe, kind of, sort of, not really, sometimes. Why not?
They change, it's not the same, it's not the.
Right, and so, again, your clocks are never gonna be 100% synchronized. And so just because this clock was a little bit earlier than this clock, well, that's not an actual indication of chronology. Okay, all it is just a way of breaking the tie. Right, and so 0 and 2 are both gonna break that tie the same way. 2 is going to conclude that 0 should continue, 0 is going to conclude that 0 should continue, they both make the same decision, 0 gets to continue. So, once you receive request, or excuse me, that okay from everybody, you can go ahead and access the resource. Now, when 0's 1, it's going to reply to a 2 with okay, excuse me, to 2, it's gonna give an okay to 2. At that point, has 2 received an okay from everybody in the network? received an okay from one right here. Right, so two is going to remember that it received that okay from one. Okay, however, it knows that it has to wait on zero, so when zero finally replies with that additional okay, well, two already received an okay from one, right, so it's good to access that shared resource at that point. Gotta wait for everybody to give you an okay. Now, we talked about this just a minute ago, who can drop off of this network and create a deadlock?
Anybody.
Anybody. Because you have to receive an okay from everybody. And so if even one node disappears, or you don't get an okay from one node, again, you have that implicit no. And so if you don't get that explicit okay, you're gonna sit there and just wait and wait. Okay. Now, if it's that susceptible to a deadlock, why would we bother using this in the first place? We have a centralized algorithm what we have to have. You got a centralized algorithm, you have to have that coordinator. Okay, so you have got to pick that coordinator, right? Or you can't run that algorithm. And we talked about the election algorithms, we'll review them here in just a second, but electing a coordinator in and of itself, that's actually kind of a complicated thing to do. And so in lieu of electing a coordinator, it may be simple to just try something like that, okay? As susceptible as it is to deadlock, because we get to skip that step of electing a coordinator. So there's give and take to everything. Now, you can also use a token algorithm, okay? This one's relatively straightforward. Here, we kind of organize ourselves in a circular overlay network, okay? Same way that we would with a distributed hash table, and we create a token. So we pass that token around. If you have that token, you want to access the shared resource, you just go ahead and access it. Okay? If you get that token, you don't want to access the shared resource, you just forward it to whoever's your successor on the server. Okay? Here, this is inherently fair. Right? Everybody is going to have a turn to access that particular shared resource. So we don't have to worry about starvation with this particular algorithm. With things like a centralized mutual exclusion algorithm, starvation could be no issue. Okay? Here, not that big of a deal. Who can create a deadlock here? Not necessarily. Yeah, whoever currently has that token. If whoever has that token is accessing that shared resource, right, or has that lock, and they drop off the network, well, they took the lock with them. Okay. So, another way of approaching that particular problem. Now, when we're talking about electing algorithms, okay, we're gonna choose a coordinator. Now, again, with this particular coordinator, there is nothing special about this particular node. It doesn't have any special hardware, any kind of special software, nothing like that. It's just a node. Okay. In the algorithms that we have looked at, and again, there's a lot of different ways of doing this, but in the algorithms we looked at, what criteria are we using to choose the coordinator? What are we looking at that is going to break the tie? It's that process ID. Whoever has the highest process ID, that's what we're trying to do. Now, let's just kind of walk through here and we'll talk about it for a second. Okay, so 7 was the coordinator, so we're just saying, you know, these integers right here, those are your process IDs. 7 was the coordinator, 7 graphic. Okay. Everybody here basically is gonna have a timer running. So what's gonna happen is somebody at some point is gonna realize that, hey, that coordinator's not there anymore. Something happened. We need to pick it. Okay, so what happens is, in this particular example, 4 is the one who realizes that the coordinator is no longer there. So it launches an election. What happens is, it sends that election message out to everybody. Okay. When you get that election message, what you do is you look at your process ID, and you determine if your process ID is higher than whoever launched that particular election. If it is, you're gonna go ahead and just reply back with an okay. If you are the node that launched that election, right, and you receive an okay after you launch the election, you're done. You don't have to do anything else. You're not the coordinator. It's somebody else's problem. Okay. If you do have a higher process ID, what you're you're gonna do is you're gonna launch your own election. Okay, so you're gonna launch your own election at that point, right? And we're going to repeat that particular process again. So here, 5 and 6 have a higher process ID than 4. 5 and 6 are both going to respond with an okay to 4, 4's done. At that point, both 5 and 6 launch their own election. So at that point, 6 is going to receive that election message from 5. Say, hey, I've got a higher process ID than you, you're done, you don't need to do anything. And at that point, when nobody else replies to 6, 6 is gonna realize, oh, hey, I'm the new coordinator. Okay, and it takes over. Now, a couple of questions here. Why might we have a situation where we have to launch multiple elections? In most election algorithms, we can have multiple elections going on at the same time. We have to pick the same coordinator in each one of those elections. A couple different reasons why we might have to do that. Why is that? First reason is, okay, network partition, right? What's a network partition? Yeah, when we lose links between certain parts of the network. So we have this network right here, okay? And we have this situation where for some reason we lost that link temporarily, okay? Network's divided. Okay, these nodes over here can still talk amongst themselves. These nodes over here can still talk amongst themselves, but those two groups cannot go back and forth between each other. It's a network partition. Okay, so when we have a network partition, we don't necessarily know who's left, who can we talk to, and who do we lose contact with. Right, so because we don't know who's left necessarily, we may have to have this election process happen multiple times before we figure out, okay, who is on our side of the partition and who did we lose. Right, so that is typically why we need to have multiple elections happening at once, right? Because we don't know who's left. We gotta figure out who's left. Okay. Now, why are we using the process ID as the criteria to choose who's gonna be the new coordinator? Because that whole process that we just looked at, that's nothing but an algorithm for finding who has the highest process ID. That's all of that stuff. So why are we using the process ID?
It's an continuous process?
Sorry?
It's continuous?
Not necessarily. We do have to have a procedure for handling the data joins network. We'll talk about that here in just a second. But that's not necessarily why we use the process ID. Why do we use the process ID? Everybody has a process. Okay. Everybody has a process ID and they're directly comparable. So we can just compare one process ID directly to another one. Somebody's gonna have a higher one. So whatever criteria you use, and you can use all sorts of criteria. You don't have to use a higher process ID, but if you do use it, you gotta make sure that everybody has that particular value. Because if not everybody has it, it's not gonna be real useful. So everybody's gotta have it, you gotta be able to compare back and forth. In addition to that, everybody is going to arrive at the same decision as to who the new coordinator becomes. Because your process ID is going to remain the same for as long as that process is active. If you're using timestamps or something like that, timestamps are gonna be a little bit different every time. Okay, and since we have multiple elections going on, we can't guarantee we're going to elect the same coordinator. But when we're using process IDs to be fixed, we can. Okay. Now, what happens is, when we have an algorithm that comes on the network for the very first time, it launches an election. Okay, so when you join the network for the very first time, you always launch an election straight away. And why do you do that? Why does the new guy have to launch an election? Right, not quite, right? That's important. I mean, again, you know, we're joining the network for the first time, we need to have some way of determining who's actually connected, who's reachable, all that reachability. Okay, so that's an aspect of it, but that's not necessarily why we launch an election immediately. The reason we launch an election immediately, it's possible that whoever just joined the network now has the highest process ID on the network. We gotta figure that out. So you join the network for the very first time, well, again, we don't necessarily know who's there. Right? So it's possible that we have the highest process ID. If we have the highest process ID, then we're supposed to be forward. Okay? That's why it's called the billing algorithm. The biggest one takes over. Okay? And Woolly out route, right? However, we're gonna do, back with the circular overlay network, ring circular overlay network. Now, still using the highest process ID, whoever has the highest process ID, but now what we're gonna do when we launch that election message, we're gonna put our process ID in that particular election message. Okay? We are going to circulate that around to everybody. Now, again, in the event of a network partition, we don't know who's left. Because we don't know who's left, well, we gotta see who's there. How does the node that launched that election know that it has gone to everyone who is reachable in that network?
When it plays its own number.
When it receives an election message and it has its own process ID in it, that means that we've gone around to everybody who's still there. Okay. Same things happen here, we're using the process ID because everybody will arrive at the same decision as to who the recorded your answer. Okay. So those are coordinated. This is the election output. All right, so that was a review of last part of chapter 6. Do we have any questions on that? Mutual exclusion election. Now, we'll talk a little bit more about arbitrary scheduling today. Okay, so let's go back and talk about audits and everything else as first thing. Okay, reasons for replication. We have two primary reasons for replication, right? What are those reasons? Why do we make copies of stuff?
To make it easy to get the resources,
Sorry?
make it easy to get the resources close to the.
Okay, so we wanna make, increase availability, that's a big thing. Okay, so increasing availability is a big thing, and what is the other reason? Other reasons, redundancy. Okay. Right, so what happens is, again, if we have this particular network here, well, let's say that we have a resource that everybody is interested in, and that resource is on that node. Okay, now if anybody wants to access that particular shared resource, well, they've got a pretty long path to go through to get to it. Okay, so that's problematic. So in order to increase that availability, what we could do is we could just potentially just make a copy of that resource. Right, we can put that in a place that's a little bit more centralized to more nodes. So for instance, based on whatever kind of criteria you wanna use, maybe you wanna put a copy of that right there. Okay. So now, pretty much everybody in that network should be able to get to that resource in less than 2 hours. Okay. Now, that's performance, right? Increases availability, right? Increases performance. Again, we have the issue of redundancy, a network partition. Okay, so again, if we have a network partition right here, and we've divided that network into 2 different pieces, well, if there was only one copy of that resource right there, everybody that's on this side of the partition just lost it. You can't get it. Okay. However, if we made a copy of it here, well, we've increased redundancy. We're increasing availability, okay, and increasing redundancy. Bad part is, okay, is consistency. Anytime we make a copy of something, the problem is that if we make a change to any one of these copies, right, because it's a full replica of a resource, so we're not just gonna be reading from it, we're gonna be writing to it, changing it, updating it, all that kind of stuff. Okay, so if we change this particular resource, right, we make some kind of update to it, well, this copy and this copy are no longer identical. And if they're not identical, well, they're not consistent, right? Because a copy is supposed to be identical. Okay. Now, the trick is, okay, when it comes to maintaining that particular replica, okay, again, it's not just as simple as saying, okay, well, we made one copy here, let's just go ahead and update that copy as soon as we make any kind of an update at all. Right, because again, it's cost, right? We have to route data along that particular path and everything else. It's not free when we do this. There's always some kind of cost. So what we do is, we have to decide when we are going to propagate those updates. Okay. Now, some of this is what's going to be called application dependent, right? So when we talk about application dependency, what are we talking about? We're talking about some applications can tolerate a lot of inconsistency and others can't. So we talk about tolerating inconsistency, what are we talking about? some applications need those copies to be 100% as often as possible. Okay? If we are doing something like finance money, you want those replicas to be 100%. Okay? If we're doing something like, a webpage, Wikipedia or something, right? If the copy of the Wikipedia article on this replica and a copy of the Wikipedia article on that replica are not 100% identical, it shouldn't kill anybody. Okay, right? I guess it depends on what article you're reading, but it's not that big a deal. It's not gonna blow anything up, right? It's not, who cares? Okay, so it's application dependent. So what we have to do, we have to determine when we wanna propagate those updates. And so what we need the ability to do is to quantify how different those two copies are. Okay, and that's where we have this whole thing about comments, right? Continuous consistency. Okay, so we have a couple of different ways we can measure these things. What these comments are, and again, comment is a consistency. Okay, so here, this comment is gonna cover these two values. It's gonna cover X, and it's gonna cover Y. Right, so X is 6, Y is 3. Now, these replicas should be 100% identical. Okay, so we have these replicas, they're spread out, we have different operations being executed on different replicas. When we are looking at this diagram, what we see here, okay, 5 in B. Okay, that character is going to be the replica where this originated. Okay, so this replica originally happened over here on this particular copy of that value. And it happened at the local timestamp block. So this was an operation that originally happened. Okay, so we have, with this nomenclature, we got your, originated timestamp that it happened. Okay, we can break this down a lot of different ways. So we're looking at our vector clocks. Okay, and our vector clock here says 15:5. What we're doing here, that first position, that 15, is always going to stand for the local time at replica A. Okay, so no matter where you see that value, it's always the same. At A, the last operation we saw at A was 14. Okay, so what we have to do when we are recording the time at A, we have to increment that counter by 1 and we record that time as being 15. Okay, why do we bump that counter forward? It's just like with vector clocks or land force logical clocks, we can't have two events happen simultaneously. So when something happens, we have to advance that clock. Okay. Now, what we have 5, okay, which is being recorded for the time at replica B. Okay, so we look at this. Here. Okay, so there's our 5, we're recording the 5 value. Okay. Now, again, like vector clocks, we have to take whatever value we received and overwrite the local value. Okay, so don't let that, I know that looks a little funky, but if we're talking about the local value, you have to advance it by 1. If we're talking about the remote value, you just take whatever you have. As far as you know, replica B, that could have been the last thing replica B ever did, and then it takes it. Okay, so we have to record what we got. Okay, over here, replica B, that position for A is being recorded as 0. Why is it being recorded as 0? So we're looking at replica B. How many operations from replica A has replica B seen? It hasn't seen anything yet. And so just like with vector clocks, because we are omniscient, we can look over at replica A and say, well, replica A has actually been pretty busy. Okay. However, because replica B hasn't seen any of that, we've got to record this being 0. We haven't seen it. Okay. And again, the last thing that replica B did, that second position is always 4, not replica B. Last thing it did was a 10. And we got to bounce that counter forward because no two things can happen simultaneously, so we record 11. Are you guys clear on how these vector clocks work? We're indicating everything else. Okay. So these vector clocks are basically just counters of operations. Right? So what we can do here, if we we are attempting to put an upward bound, okay, on the amount of consistency, we're gonna say, well, hey, if this counter advances further beyond that particular counter, that means I have more activity on one replica that has not been updated on the other replica. We need to bring those two things in line with one another. So we're establishing that upper bound. Okay. Order deviation. When we are looking at these diagrams, if something is grayed out in this diagram, we say it's been committed. And when we say committed, what do we mean? Committed means it's been written into quote-unquote permanent storage. Okay? The literature uses that term. That doesn't mean that it's chiseled in granite. What it means is it's been written to non-volatile storage. It's not convenient to change. Okay, if this were still sitting in main memory, we could rearrange things real easily. If it's committed, well, now that, operation has increased in cost. Okay. So, what order deviation is, that is the number of operations that are still sitting in memory that we can rearrange if we need to. Okay, so replica A here has got these 3 operations right here. So if we needed to, we could rearrange those operations however we wanted to. Okay, so it says the order deviation there is 3. Okay, over here in replica B has not committed anything yet. And because it hasn't committed anything yet, we say the order operation, this is order deviation. Okay. Numerical deviation, that first position right here is what is called numerical deviation with respect to operation. What that means is how many operations have originated at the remote replica that we have not actually seen at the local replica. So we're looking at replica A, okay, how many operations from replica B has replica A received? Yeah, just the one. It's just that 5B right there. That's the only one it's seen. So how many operations have it not received? Yeah, just the one. So that's where that 1 comes from. Okay, so numerical deviation with respect to operation over here is 3. How many operations that have originated at replica A that replica B has seen? Haven't seen anything yet from it. Right? So there's 1, 2, 3, and then over here in replica A, so we say numerical deviation with respect to operation, 3. It's 3 operations we haven't seen. Okay. The other one is numerical deviation with respect to value, which is a little easier to demonstrate. You might prefer to. So let me go ahead and bring up another example so we can view this one by hand. Alright. So we're set up to the other one. The only difference here is I've added these committed, okay, so everything else is pretty much works the same way. Okay, now, over here in replica A, what do we, let's take a step back, let's do this one first, okay? So, here in replica A, what is gonna be the vector clock for this first position? What's the last operation that originated at A? Or 14A is the last thing that originated here. So we're gonna take that value, and because we can't have 2 events happen simultaneously, it's going to end up being 50. Okay. And I'll leave these up here in case you guys want to take pictures of them later. I know my handwriting is not the easiest to read, but it's on, I'll be over here. What was the timestamp on the last operation that we received from B? Okay. So, again, we're just looking at what A is seeing. Don't pay any attention to this stuff over here. What was the last thing that we saw from B over here in A? That's that 5B. Right, that was the last thing that we saw. So that's the last thing that A saw. So far as A knows, that's the last thing that we ever did. That's what we record. What was the first number? 15. Okay, so that's 14 right here. So we add 1 to it, we get 50. And over here at B, that first position, because it's a vector clause, is always going to reflect the time at A. So what was the last operation A saw from B? Yeah, 12. Okay. So because that is a remote operation, B is going to make the assumption that's the last thing that A ever did. So it's going to go ahead and record. Okay.
Why don't you add one?
We add 1 when we're incrementing the local counter, right? Because we're the local counter, we know that we haven't died yet. And so, because we can't have 2 events happen simultaneously, we bump that counter forward by 1. That's what we do. Okay. I think that's just convention, that's what this system does. Okay, so, for the B here, this is the local counter for B now. What was the last operation we saw originate at B? That 8B, right? So we're gonna take that 8, and because this is the local counter, and have 2 events happen simultaneously, bump that forward to 9. Okay. Order deviation. What is the number of operations we can rearrange at A if we wanted to? So we have these 2 events that are committed, they've been written to non-volatile storage, we're not gonna screw with them. These white events here, the ones that haven't been grayed out, those are still sitting in main memory, so we can reorganize them if we want to. I'm gonna say order deviation. Over here, what's the order deviation here? Just 1. Numerical deviation with respect to operation. How many operations have occurred at B that replica A has not seen yet? There's 2 operations that have happened at B, 5B, 8B. Over here, replica A has seen that 5B, hasn't seen the other one. So we're gonna say there's 1 operation that we haven't seen yet.
Can you explain that one time?
Okay. So what happens is, we have 2 operations that have originated at B. We got 5B, we got 8B. Okay. What that value does is called numerical deviation with respect to operations. There's 2 operations that have originated at B. When we're looking over here at replica A, how many of the operations that have originated at B that A has not seen yet? It's seen this one, which is 5B. Has it seen that 8B yet? No, so we record that as being 1 operation we haven't seen. Okay. Right, so numerical deviation with respect to operations. How many operations from A has B seen at this point? Just that 1, right, that 12A. How many operations have actually originated at replica A? How many?
3.
Yeah, 1, 2, 3. Now, trick is, where did that 8A go? Who knows? Stuff gets lost. Okay, it's a network. Right, so stuff gets delivered out of order, stuff gets lost, has to get reset. But there's still 3 operations at A total, B's only seen 1 of them. So because there's 2 operations it hasn't seen yet, 2. Okay. Okay, now, this next one, numerical deviation with respect to value. This is the one that's kind of difficult, based on how the book has it set up, which is why I drew this. What we are going to do, we are going to compare what has been committed locally to what is presently in memory remotely. We're gonna compare the X's to the X's, the Y's to the Y's, and we're gonna take the largest difference. So the difference between the X's is 0, the difference between the Y's is 4, guys clear on why these values are what they are? Yes.
Explain the numerical deviation again.
Which one, the first one or the second?
The second one.
Okay, so that's numerical deviation with respect to value. Okay, what we're doing is, we have stuff that's been committed locally, that's been written out to non-volatile storage, we don't want to change. So what we're gonna do is we're gonna compare the last thing that we have written to permanent storage locally against what is presently sitting in memory remotely. Because we gotta, the X and the Y are the two values that we're quantifying the inconsistency. So what we're doing is, we're gonna compare the X's to the X's and the Y's to the Y's. We're gonna take the largest difference, so the difference between the X's here, X equals 2, difference is 0. Okay, here, Y equals 2, Y equals 6, difference is 4. So that's what we record, 4. Okay, so now we're looking at the actual value, the content of that particular memory. Okay. So these are all just slightly different ways of quantifying how these two values are different. Okay, so the easiest thing to do would probably just be look at the values in memory and say, okay, well, the values, this one is, this much different than the other one. Okay, but they may not necessarily be integer values. Right? If they're integer values, that comparison is pretty straightforward. If they're, characters or something, how you're gonna say one character is greater than the other character, right? That doesn't necessarily make any sense. So we need to have other ways of quantifying that consistency. You guys wanna do another example? And again, guys, a lot of this stuff is just convention, right? So this is just how this particular system works. They have their reasons. So if you're thinking, well, why couldn't we just do this or this or this? Well, you probably could. What I'm explaining is what's particularly presented in the text. Okay, so similar kind of thing to what we have going on here earlier, sorry. See this? Okay, vector clock at A. What was the last operation that happened at A? Yeah, it's gonna be that 14. So because this is the local counter, we can't have two operations happen simultaneously locally. So we're gonna bump that forward, and end up being 15. What was the last operation that A